The final is matrix multiplication. This is a little tricky. Matrix multiplication follows a particular order, and you need to follow that particular order. Any random order will not work. So let's say I have a matrix P, which is represented by Pij, where I represents the rows of that particular element and J represents the column of that particular element. And let's suppose M cross N is the dimension of P matrix. Suppose I have another matrix, Q, whose elements are represented by Qij, where again I is the row of that particular element, J is the column of that particular element, and we have dimension N cross P. The condition is, as we know, M is the number of rows, N is the number of columns over here. And here, N is the number of rows and P is the number of columns. So let me mark it over here as well. We need to ensure that if I am multiplying P with Q, then the number of columns of P must be the same as number of rows of P. This is true for PQ. However, if we are to talk about QP, that is, I am multiplying this with this, then the reverse must hold. That is, the number of columns of the first matrix must match the number of rows of the second matrix. So in this case, we need to make sure that we know which are we multiplying with what. So in matrix multiplication, because in normal multiplication, 2 times 3 is the same as 3 times 2, right? 2 times 3 is also 6 and 3 times 2 is also 6. It doesn't matter what we put in front of what. But this does not hold in terms of matrix algebra. A, B. Let's suppose A is a matrix and B is another matrix. We multiply A, B. That need not necessarily be the same as B. AB need not be the same as BA. They may be different. They might, of course, be the same. There are conditions under which they might be same, but they need not necessarily be same. You might get A and B such that AB is not the same as BA. So you need to make sure whether you know that you need AB or whether you need BA. Based on which direction you're going, whether you're going AB or BA, essentially the number of columns of the first matrix, or that is the matrix on the left, has to be equal to the number of rows of the second matrix, that is the matrix on the right. So that is how you can calculate the matrix multiplication. Another thing is, as we had mentioned before, if we look at matrix addition and matrix subtraction, the two statements that we were talking about was what is the condition of the dimension of the two original matrices and what is the dimension of the resultant matrix. So for matrix multiplication, we have already discussed what is the condition for the dimension of the two original matrix. The next question comes, what is the dimension of the resultant PQ matrix? The resultant matrix's dimension will be the row for the first element and the column number for the second element. So the row of the first element and the column number for second element. If it's M cross N, N cross P, then the dimension will be M cross P. So that's the dimension of the resultant matrix multiplication. Now, how do we define it? If we look at this statement, at first it will look really scary because I have written it in summation. It might look, of course, you might be used to this notation. If you're not used to this notation, you will get used to it. It's a summation notation. It might look scary, but believe me, it's not that difficult. It's pretty easy. So let's suppose we have Cij. Again, as I have mentioned before, the dimension will be M cross P. If we are talking about P having dimension M cross N and Q having dimension N cross P, then C, which is PQ, that will have dimension M cross P. And it's given by summation k equal to 1 to M, the number of rows, that is k equal to 1 to M, P, I, K, Q, K, J. So we look at the row first and then we look at the column of the second matrix. The row of the first matrix, this is the first matrix, so this is the row of the first matrix, and we look at the column of the second matrix. So sum of the product of the element is row for first matrix and column for second matrix. Now let's look at an example. Let's suppose I have a matrix A, or rather going by the definition that we had talked about, let's suppose this is matrix P and this is matrix Q, and we need to find some matrix C. So the first thing is we need to look at the dimension of the original matrix, and we need to decide what will be the dimension of the final matrix. So let's look at the first question. P matrix has 2 rows and 3 columns. So the dimension of P matrix is 2 cross 3. Q matrix has 3 rows and 1 column. So its dimension is 3 cross 1. Now let's look at the number of columns of the first matrix, that's 3, and the number of rows of the second matrix, that's 3. So 3 and 3, that matches. So the first condition holds, that is, we have the number of columns of the first matrix is equal to the number of rows of the second matrix. So the first condition holds. Now we need to decide what will be the dimension of the resultant matrix. So what will be the resultant of the, what will be the dimension of the matrix if we multiply these two matrices? So the dimension of P is 2 cross 3, that is, it has 2 rows, and the dimension of Q matrix is 3 cross 1, that is, it has 3 columns. So for the resultant matrix, it will have the number of rows equal to the first matrix and the number of columns equal to the second matrix. So that will have 2 rows and 1 column. That is, it has 2 cross 1 dimension. Let me just mark that properly. It has 2 cross 1 dimension. That means we need to find out 2 elements, this element and this element. For the timing we don't know, we need to find out how to do it. Now let's look at some colors. Let's take a different color because it will be easy to note then. And let's increase the thickness as well. So what I usually do is I use my finger and I first look at this direction and then I look at this direction. So I first go horizontally for the first matrix and vertically for the second matrix. Now, if we go horizontally, since we had said that the 3 elements are essentially, what do we mean by 3? Essentially, it has 3 columns, which means every row has 3 elements. And what do we mean by this 3? This 3 essentially means that it has 3 rows, that is, each column has 3 elements. So if we look at the row here, the rows have 3 elements and the columns also have 3 elements. So what we do is we essentially look at this element and this element. So that's 2 times 7. So we first write 2 times 7. Since we are moving in this direction, the next element we'll be considering is 3. And in Q, we are moving vertically down. So after 7, we'll have 2. So we have already done 2 and 7. The next element we'll be talking about is 3 and 2. So 2 times 7 is the first. The next will be 3 times 2. That is 3 times 2. Moving further vertically for the first matrix, moving further horizontally to the right, for the first matrix, we'll have 4 as the next element. And further vertically down for the second matrix, we'll have 6 as the next element. So we have already done 2 cross 7, 2 times 7 rather, 2 times 7 plus 3 times 2 plus 4 times 6. So 4 times 6. So what we essentially do is, for every element on the first matrix, we multiply the particular corresponding element along the corresponding direction and multiply these two. Since the number of elements on the rows of the first matrix is the same as the number of elements along the column of the second matrix, we'll have that many products on the element for the elements of the resulting matrix. So we have 3 elements for each row of first matrix and 3 elements for each column of second matrix. So we'll have 1, 2 and 3 elements to be added. Now, which are the elements that we form? We take one element from the first matrix and multiply that with the corresponding element of the second matrix. So this essentially incorporates both addition and multiplication. So we first take this element, multiply that element, keep it aside. Take the next element, multiply it with the corresponding element of the second matrix, add it. Take the next element from the first matrix and the corresponding element from the second matrix, add it. So each pair, let's mark this as one pair, this as the next pair, and this is the third pair. Each pair has product and we add the pairs. So essentially we add product pairs. So let me write that down if that's easy to remember. We'll be adding the product pairs. So this might help to remember the order of operations. So sometimes students might get confused. What do we do first? Do we add or do we subtract? So essentially we add the product pairs, which means we first multiply each product pair. Sorry, we multiply each pair of elements and then add the product of these pairs. And that is how we get the first element. Similarly, we can also have the other elements. Let's take a different color this time. So let's say we can take blue. Next, we take the second row. And since we have just one row here, we go along the same row. We'll have 4 times 7. So 4 times 7, that's 4 times 7 over here. Moving further horizontally towards the right, the next element is 6. We multiply 6 with 2 and add. The next element is 5. Then we add, then we multiply 5 with 6 and we get 5 times 6. Sorry, this would have been times 6. Let me just use a pen or pen. This will be 5 times 6. So we have 2 times 7 plus 3 times 2 plus 4 times 6, that's 44. And 4 times 7, that's 28. 6 times 2, that's 12. And 5 times 6, that's 30. So we have 24 plus 12 plus 30, that's 70. Now, the question that might come to your mind is, what do we do if we have more elements? So essentially, let's suppose you have some more elements, 2, 3, and 5. Let's suppose you have another. So this has dimension 2 cross 3, and this is dimension 3 cross 2. So the first thing that will come to your mind is, so yeah, 3 cross 3 matches. That is the number of columns in the first matrix is equal to the number of rows in the second matrix. Then what will be the dimension of the resultant? Since I am talking about 2 rows in the first matrix and 2 columns in the second matrix, the resultant will have 2 cross 2. That is, it will have 2 more elements. Let me just write that down properly. 2 cross 2. It will have 4 elements. That is 2 more elements over here. How will I calculate these 2 elements? Essentially, we have one column over here, we are moving just along the same column. But when we move along the second column over here, you take the second column, that is the row element corresponds to the row elements of the first matrix. So if we are trying to calculate the first row first element, then we'll take the horizontal direction of the first matrix's first row, and since it's the first column, so in the second matrix we'll take the first column of the matrix in the vertical direction. So if let's take a thinner pen so that I can write. Let's suppose I'm talking about Cij. Okay, so we need to find out the Cij element of the product. Let's suppose C is product of P and Q. We need to find Cij. So you will take the ith row of the first matrix and go in this direction, and you take the jth column of the second matrix and go in this direction. So naturally you will find all the matrices of that element. Whatever element you want to calculate, you will take that particular row for the first element for the first matrix and that particular column for the second matrix. So for the ith row, you go in this direction, and for the jth column, you go in this direction. Which row and which column, it will take some time, but if you want, you can again revisit this video and it will become easier. With practice, it will become easier. So that's how you do matrix multiplication. Similarly, I have a second example here. So let's suppose I have a matrix 6, 4, 9, 2, 3, 6, another matrix 1, 2, 3, 4. Now let's check the first condition. That's the number of columns of the first element, first matrix must match with the number of rows of the second matrix. So that matches. If that is the case, then what is the dimension of the resultant matrix? So that will be number of rows of the first matrix and the number of columns of the second matrix. So that will be 3 times 2. So let me write that down here. That will be 3 times 2. Now let's again move in the same direction. That will be 6 into 31. So let's take an arrow pen or let's remove, yeah. So we'll move in this direction for this matrix and this direction for this matrix. So it'll be 6 times 1 plus 4 times 3. So that's 6 times 1 is 6, 4 times 3 is 12. So that's 6 plus 12, which is 18. This element is done. Next, we want to find out this element. What is this element? This element corresponds to the first row and second column. First row and second column. So this is C1, 2. So we look at the second column of the second matrix and the first row. So this is the first row and we look at the second column. So it's 6, 4 and we look at 2, 4 here. So it's 6 times 2 plus 4 times 4. That's 12 plus 16. So it's 12 plus 16. This element is C21. So let me write that down. This is C21. So we look at the second row and the first column. So it's 9 times 1 into plus 2 times 3. So it's second row, first column. 9, 2, 1, 3. 9 times 1, 2 times 3. So that's 9 times 1, 2 times 3. That's 9 plus 6, which is 15. Again, the C22 element, that will be the second column, second row. So 9 times 2 plus 2 times 4. That's 18 plus 8, which is 26. C31. So this is C31. So the third row of the first matrix and the first row of the first column of the second matrix. So we'll be talking about 3, 6 and 1, 3. So 3 times 1, 6 times 3. 3 times 1 plus 6 times 3. That is 3. 6 times 3 is 18. So 3 times 1 plus 6 times 3, that's 3 plus 18, which is 21. Finally, the C32 element, that is C32. So that's the third row of the first matrix and the second column of the second matrix. So we have 3 times 2 plus 6 times 4. That's 3 times 2 is 6. 6 times 4 is 24. So 3 times 2 plus 6 times 4 is 6 plus 24, which is 30. So that is how we do matrix multiplication. So now there are certain notes that we need to note. As I have mentioned before, AB is not the same as BA in general. This property, the fact that AB is equal to BA in normal algebra, if we talk about 2 times 3 is the same as 3 times 2, this property, this is not just for matrix, this is not just for normal multiplication, it is also true for addition. So 2 plus 3 is the same as 3 plus 2, right? 2 plus 3 is also 5, 3 plus 2 is also 5. This property, the fact that the order can be interchanged, this property is called commutativity property. This commutativity property, this does not hold in matrix. This might not hold in matrix algebra, to be very precise. It might hold in certain cases, but in general, this property, this commutativity property, the fact that orders can be interchanged, does not hold. So the order is of prime importance. AB is not the same as BA. So if you multiply this matrix, you actually won't be able to multiply 1, 2, 3, 4 with this matrix in the reverse order, because then it will be 2 and the number of columns of the second matrix will be 3. Sorry, the number of rows of the second matrix will be 3, which is not matrix multiple. It's not possible to multiply these two matrices. So the order of the matrices, essentially because of the dimension factor, the order is of prime importance. The next note that we need to make is ABC equal to BAC, and A times B plus C is equal to AB plus AC. So this is the associative property and this is the distributive property. And these two properties actually hold in case of matrix algebra. So we need to remember, if we, So commutativity property might not hold in case of matrix algebra, but associativity property and distributive property holds for matrix algebra. So AB might not be equal to BA, but AB times C might actually be, or it's actually is the same as A times B, and A times B plus C is also the same as AB plus AC. So these concludes the operations of matrix addition, matrix subtraction, and matrix multiplication in both scalar form and matrix into matrix form.